Welcome back to Tech Tangents, your favourite STEM podcast. Today we're diving into a topic that might seem purely based on luck, but beneath the flashing lights and spinning wheels lies a fascinating world of mathematics.
Yeah, we received a few requests from our last episode to make them slightly less technical. That one was quite tricky. So we thought, what other way to make it up to you than to discuss how you can gamble statistically and the maths behind it?
That's right, Rowan. But before we start, as promised, let me test you on our last episode. What does MILP stand for?
Is it mixed integer linear programming?
Well done. That's correct.
Now, for my turn, how do you pronounce that guy? You know, the one who did all the algorithms?
I've got to get it right this time. Dijkstra.
Yes! Finally.
Anyway, for all you STEM enthusiasts out there, prepare to have your perception of gambling completely transformed. Every card dealt, every dice roll, every spin of the roulette wheel is governed by mathematical laws.
Yeah, and you guys might be wondering, how is that? What do you mean, mathematical laws? Pranav, can you enlighten us with some of your plans?
Okay. So basically, we're going to be breaking it down into 8 key statistical concepts that reveal just how maths works in this case. We'll give you clear definitions, real-world gambling examples, discuss those tricky edge cases, and even touch on how casinos and those rare advantage players actually use these principles.
Think of it as peeling back the layers of chance using analogies, where we talk about coin flips, drawing imaginary urns, and even walking on a statistical board game to make these ideas really stick.
And we won't just leave you there with dry theory. We'll share some captivating stories, anecdotes of gambling pioneers like Claude Shannon, Ed Thorpe, and how mathematics has empowered both those trying to beat the system and the houses that are built on it.
I'm glad those names are a bit easier to pronounce. Let's kick things off with a fundamental concept, the law of large numbers.
In simple terms, the law of large numbers, or LLN, as I would like to call it, states that if you play an independent game repeatedly, the average outcome of your plays eventually gets closer and closer to the game's expected value. What would be a nice way to phrase that?
So you can think of it like this. Imagine flipping a perfectly fair coin. In the short run, you might see a streak of heads or a streak of tails. It feels a bit random and unpredictable.
Exactly. You might win a few rounds in a row, or you might lose a few. But the LLN tells us that if you flip that coin thousands and thousands of times, the average result per flip will settle down to around 50% heads. Those early winning or losing streaks might become less significant in the grand scheme of things. So you can think of it as time progresses, as time reaches, infinite or thousands in this case, the probability becomes 50% for both heads and tails.
So now let's get a bit more formal with that. Mathematically, if we have a series of independent and identical random variables, so let's call them x1 and x2, and you go all the way up to xn for n number of numbers. Each of these has an average outcome, or mean, that we'll call E of x, that's the expected value. And then as the number of trials, n, gets really, really large, the probability that the average of all those outcomes, so that's the mean, that's going to get really close to the expected value, E of x, which approaches 1.
So while that looks a bit technical, the core idea is that the more you play, the more your average winnings or losses per game will mirror the inherent design of the game or the expected value.
And this is where casinos have a significant advantage. They design their games so that the expected value of any bet you make is slightly in their favour. It's a negative expected value for the player, but what happens then?
The law of large numbers then guarantees that as gamblers play more and more, their average loss per game will inch closer to the negative expected value. So even if you get lucky in the short term, winning a few hands or hitting a small jackpot, the long-term trend, thanks to LLN, is towards the house's advantage. So don't just get too happy if you just win a few rounds at the start, yeah?
Yeah, that's the commonly known phrase, the house always wins. The house will always have the advantage in the long run. So let's take an example. Imagine a game with a fair six-sided dice. If you roll a 1, 2, 3, 4, or 5, you win $1. But if you roll a 6, you lose $6.
To calculate the expected value here, we take the probability of each outcome multiplied by its value and sum them up. So it's 1 over 6 times by $1 plus 1 over 6 times by $1. You do this 5 times, so you get 5 over 6 times by $1 plus 1 over 6 times by minus $6 because you're losing $6 if you roll a 6. And if you sum that, you get minus 1 over $6.
Yeah, so that means on average you expect to lose about 16.67 cents every time you play this game. Now, if you only play it twice, you might win both times and come out ahead. But the law of large numbers tells us that if you play thousands or millions of times, that your average loss per game will get very, very close to that 16.67 cents.
This leads us to the common pitfall, the gambler's fallacy. How interesting does that sound? This is the mistaken belief that if a fair game has a certain outcome repeatedly, like flipping 9 heads in a row, the opposite outcome, a tail, is somehow due to balancing things out. Wait, but does the law of large numbers work that way?
No! Each coin flip, each dice roll, each card dealt in a properly randomized game is an independent event. The past doesn't influence the future. The law of large numbers only guarantees that the averages converge over a huge number of trials, not the individual events that will even out in the short term.
Think of it this way. The law of large numbers is about the long-term destination of the averages, not about the correcting short-term deviations.
There are some exceptions to the law of large numbers. It relies on the game being independent and having a finite expected value. If the outcome of the games are linked, or if the potential payouts are theoretically infinite, like in the famous St. Petersburg paradox, then the law of large numbers might not behave as we expect.
For gamblers, the key takeaway from the LLN is this: you cannot outsmart a game with a negative expected value by simply playing longer. In fact, the more you play, the more likely the house edge will manifest in your results. It also highlights the need for a significant bankroll to weather the inevitable ups and downs of short-term variance.
So for casinos example, the law of large numbers is their bedrock. With a large volume of bets, they can be highly confident that their actual win rate will closely match the expected win rate they've built into their games. That seems pretty fair, doesn't it?
Yeah, sure. Moving on, let's talk about the central limit theorem, or CLT.
So the central limit theorem is another incredibly powerful concept in statistics. It basically says that if you take the sum or the average of many independent, identically distributed random variables, that the sum or average will tend to follow a normal distribution, which looks like a bell curve.
And the really amazing thing is, this holds true regardless of the shape of the original distribution of those individual variables, as long as that original distribution has a finite variance.
So imagine tracking your total winnings after playing the game many, many times. The payout of a single round might be quite skewed. Maybe you usually lose a little but occasionally win big. However, as you play more and more independent rounds, the distribution of your total winnings will start to look like that symmetrical bell curve centered around the overall expected value, or the mean.
The CLT helps us understand why this happens and allows us to approximate the probability of certain cumulative events, like the chance of being up or down by a certain amount of large number of bets.
Casinos heavily rely on the central limit theorem to predict their long-term earnings and to set aside appropriate reserves. For example, the payouts from slot machines can be very skewed, with lots of small losses and very few large jackpots. But when you look at the total payout across thousands of spins, the distribution becomes approximately a normal one. This
allows casinos to calculate the confidence limit, which is essentially a range within which they can be highly confident their total winnings or losses will fall over a given period. It helps them manage risk. What was the other implication again?
So the central limit theorem also has implications for advantage players. For instance, a card counter in blackjack might have a slightly positive expected value per hand. After many hands, the central limit theorem can help estimate the probability that their total earnings will exceed a certain target, assuming a normal distribution of their cumulative winnings.
Let's consider our early die game again, where you have a high chance of losing a little and a small chance of winning a lot. The payout distribution for a single roll isn't normal at all. But if you play that game 1,000 times, the central limit theorem tells us that the distribution of your total winnings will be approximately normal, with a mean of around minus $166.67, 1,000 times our earlier expected value of minus $1/6, and at a certain spread or variance. This allows to estimate the probability of, say, breaking even or being down by a large amount after those 1,000 plays.
It is important to note that the central limit theorem relies on each player having a finite variance. If a game has extremely rare but massive jackpots, that's what we call heavy-tailed payout distribution. The variance might be infinite or just very large. In such cases, the convergence to a normal distribution can be very slow or may not even happen in the way we intuitively expect. What was the research behind this?
Some research has shown that for certain types of slot machines with very skewed payouts, the common rule of thumb of needing around 30 independent trials for the normal approximation to be good might not be enough. Casinos sometimes have to rely on computer simulations to get a better handle on the probabilities in these more extreme cases.
Yeah, so from a casino's perspective, the central limit theorem provides a level of comfort. They can design games with a very small house edge, and because of the large number of bets placed, they can still be quite confident that their actual profits will fall within a very predictable range around their expected profit. So what would that mean for you if you're a gambler?
Nice. As the gambler, the CLT means that over many bets, the total outcome is more likely to be somewhere near the overall expected loss due to the house edge, with a predictable amounts of variation. This helps in understanding the potential for large swings in your bankroll.
Yeah, so you could think of it like taking many independent measurements of something. Each measurement might have a bit of error, but if you average a large number of those measurements, the result will be very close to the true value, and the distribution of those averages will follow a normal bell-shaped curve. Similarly, each gamble has its randomness, but the sum of many independent gambles behaves in a more predictable, normal way.
Before we move on, what is a heavy-tailed payout distribution? Make sure you're answering the poll that will be on Spotify. Next up, we have hypergeometric distribution. Now, this one is particularly relevant to card games, so make sure you hear this out.
Yeah. The hypergeometric distribution describes the probability of getting a specific number of successes when you're drawing a sample without replacement from a finite population.
Let's say you have a standard deck of 52 cards, and within that deck there are 4 aces. These are 4 of our good cards. If you draw 5 cards from this deck, the hypergeometric distribution tells you the probability of getting exactly a certain number of those aces in your hand.
Yeah, and the key here is without replacement. The key is what?
Without replacement.
Exactly. Once a card is drawn, it's gone. It's not put back into the deck. This means the odds change with each card you draw, which is different from scenarios where you do replace items after drawing them.
Mathematically, if you have a total of n items, like 52 cards, so in this case, we'll call it big N. So big N, for example, equals 52 because we have 52 cards. And G of them are good, like the 4 aces I said before. And you draw a sample of n items. And this is, let's call it little n. The sample will be little n. For example, 5 cards. And the probability of getting exactly k good items, say k aces, is given by a specific formula involving combinatorics or combinations. The probability mass function of x at k is given by the binomial coefficient of g and k multiplied by the binomial coefficient of big N minus g and little n minus k, divided by the binomial coefficient of big N and little n.
So that was a bit complicated. So in simpler terms, the probability that the random variable x equals k is equal to the number of ways to choose k items from G multiplied by the number of ways to choose little n minus k items from big N minus G, all divided by the number of ways to choose little n items from big N.
Well, then you might as well just say P of x equals k is G choose k times big N minus G choose little n minus k all over big N choose little n. That was a bit simple, wasn't it?
Just a bit. Anyway, those bracketed terms with the numbers on top and bottom are called binomial coefficients. For example, kg. We said as G choose k represents the number of ways you can choose k good items from the total of G good items. Similarly, little nk big Ng is the number of ways to choose the remaining little nk items from the big Ng bad items. And the little n big N or big N choose little n is the total number of ways to choose n items from the entire population of big N items.
So in our ace example, if you wanted to know the probability of getting exactly 2 aces in a 5-card hand, G would be 4, which is the number of aces. Big N would be 52, which is the total number of cards. Little n would be 5, the cards drawn, or our sample size from the total number of cards. And k would be 2, the number of aces we want. Plugging those numbers into the formula, it would give you the exact probability.
Many card games rely heavily on these hypergeometric probabilities. In poker, for instance, the odds of getting a flush or any specific hand are calculated using this distribution, considering the number of cards of each suit and rank in the deck.
In blackjack, especially if you're keeping track of the cards that have already been dealt, card counting, the probability of the next card being a high card or a low card changes because those dealt cards are not replaced. The hypergeometric distribution helps you understand these shifting odds based on the remaining composition of the deck.
Even lotteries where winning numbers are drawn from a fixed pool without replacement follow a hypergeometric-like principle.
Now it's interesting to compare the hypergeometric distribution to the binomial distribution. The binomial distribution describes probability of success in a sequence of independent trials, where each trial has the same probability of success and the outcomes are independent of each other, which usually implies replacement.
N. If the total population size, big N, is very large compared to the sample size, little n, then the hypergeometric distribution behaves very similarly to the binomial distribution. In that case, removing a few items doesn't significantly change the overall probability of success on subsequent draws.
Imagine drawing just one card from a deck of 100 cards, where 30 of them are success. So the probability of success is 30 of 100, right? Which is also 30%. If you use the binomial approximation, you treat each draw as having an independent 30% chance of success with a large deck and a small draw. The difference between the hypergeometric without replacement and binomial with replacement effectively becomes negligible.
However, if you're drawing a significant portion of the deck, the without replacement aspect of the hypergeometric distribution becomes crucial. For example, if you're drawing a 6-card hand from a total of only 20 cards, the probabilities change dramatically after each card is drawn.
One fascinating aspect is the expected value, or EV, as we said earlier on. In a hypergeometric distribution, the expected number of success you'll draw is simply little n times G over big N, which is the same formula you'd use for binomial distribution. This is a consequence of the linearity of expectation, which we'll discuss next.
For gamblers, understanding hypergeometric probabilities is fundamental to strategies like card counting. By knowing which cards have been dealt, they can use this distribution to estimate the increased probability of certain value cards remaining in the deck.
Casinos, on the other hand, often employ countermeasures to minimize the impact of this information. Frequent shuffling of the cards, or using multiple decks, effectively resets the population big N and reduces the player's ability to gain an edge through hypergeometric reasoning.
This brings us neatly to the concept of expected value, or EV, as we mentioned before, and the powerful principle of linearity of expectation.
The expected value EV of bet is essentially the long run average outcome of how you can anticipate from making that bet repeatedly. It's weighted average of all possible payoffs, where each payoff is weighted by its probability of occurring.
Mathematically, if you have a random payoff x, for example, they can take different values, so like xi, with corresponding probabilities, pi, then the expected value of x, denoted as ex, is calculated as the sum of each possible payoff multiplied by its probability. So you go, the expected value of x is I sigma probability of xi.
The EV tells you how much you can expect to win or lose, on average, each time you play the game in the long run.
Let's revisit our die game once again. You win $1 with a probability of 5 out of 6 and lose $6 with a probability of 1 out of 6. The expected value we calculated was minus $1 over $6. This means that for every game you play, you can expect to lose about 16.67 cents in the long run.
Now, the linearity of expectation is a remarkably useful property. It states that the expected value of the sum of two or more random variables is equal to the sum of their individual expected values, regardless of whether those variables are independent or dependent. So, E of x plus y is equal to E of x plus E of y. Seems pretty simple, doesn't it?
This has a powerful implication for multiple bets. If you make two independent bets, one with an expected value of mu1 and another with an expected value of mu2, then your expected value of your total winnings from both bets is simply mu1 plus mu2.
Even if the outcomes of the bets are related, the linearity of expectation still holds. For example, if you draw two separate 5-card hands from the same deck without replacing it, the expected number of aces in the first hand plus the expected number of aces in the second hand is equal to the expected number of aces in the first hand plus the expected number of aces in the second hand, calculated individually.
Yeah, you can visualize the expected value as sort of a center of gravity of the payoff distribution. Even though you might never actually win or lose exactly the expected value of a single play, like losing $0.1666 in one go isn't possible, it's the average around which your actual wins and losses will fluctuate over many, many plays. A fair game is defined as one with an expected value of 0. Any game with a negative expected value for the player gives the house an edge, like games in casinos. Consider a simple coin flip game where heads win you $10 and tails make you lose $8. The expected value is 0.5 times by $10 plus 0.5 times by minus $8, which equals $1. So on average, you actually expect to profit $1 per flip.
In blackjack, the expected value for a basic strategy player is around minus 0.5% per dollar bet. That's the house edge. However, a skilled card counter who can identify situations, which will hopefully be you guys after this podcast, where the deck composition is favorable, might be able to create a positive expected value, saying plus 1%. In that case, the expected gain would be plus 1% of their total bets over the long run.
Because of the linearity, if you place multiple bets with known expected values, you can simply add those expected values together to find the total expected value of your overall betting session. This is crucial for analysing complex bets like parlays or when participating in multiple games simultaneously.
It's important to remember that the expected value does not tell the whole story. It ignores the variance or the size of the potential swing in outcomes. A lottery might have positive expected values due to a very large jackpot, but the probability of winning that jackpot is often incredibly small, leading to huge volatility.
Yeah, expected values is a long-run concept. You might get lucky and win big on a single game, even a game with a negative expected value. Over many, many plays, the expected value will tend to assert itself.
Just like we discussed in LLN.
Exactly. If a game has a negative expected value for the player, the more you play it, the more likely you are to lose money.
Advantage gamblers are constantly searching for situations or promotions that offer a positive expected value. This could be exploiting a casino bonus, finding a better market with mispriced odds, or, as you mentioned, card counting in blackjack. They often use a concept of EV, or expected value, to determine how much to bet in order to maximize their long-term growth. A strategy we'll touch on later with Kelly criterion.
Casinos, on the other hand, ensure that the expected value of virtually every game they offer is negative for the player. This built-in house edge, combined with the law of large numbers, is the fundamental reason why casinos are always profitable in the long run.
Let's delve into Bayesian inference, a powerful tool for updating our beliefs in the face of new evidence.
At its core, Bayesian inference is how we revise the probability of a hypothesis being true based on the data we have. Bayes' theorem gives us the mathematical framework for this. The probability of the hypothesis given the data is equal to the probability of the data times by the probability of the data given the hypothesis times by the probability of the hypothesis.
Let's break that down. Probability of the hypothesis represents our initial belief about the likelihood of something. You can call that the critical value or the expected value. This is called the prior probability, to be more precise. Then we observe some data. That is the probability of the data given the hypothesis. It is the probability of seeing the data if our hypothesis were true, if we have to reject or accept our hypothesis. This is the likelihood of something happening, or something we want to happen. The probability of the data is the overall probability of observing the data regardless of the hypotheses. And finally, probability of the hypothesis given the data is our updated belief about the hypothesis after seeing the data. This is the posterior probability. So remember the terms prior and posterior probability.
That's interesting, but where specifically is it used in gambling?
In gambling, Bayesian inference is particularly useful when the true odds of something happening are unknown or uncertain. Historically, gamblers have used this to try to exploit potentially biased games. Do you want to reveal our classic example now?
Yes, and that is the example of Joseph Jagger in 19th century Monte Carlo. He noticed that one particular roulette wheel seemed to land on red much more often than expected. His initial belief might have been that the wheel was fair, equal probability for all outcomes. But as he observed more and more red results, a Bayesian approach would lead him to update his belief, increasing the probability that the wheel was biased towards red. He then bet heavily on red and famously broke the bank.
So a Bayesian gambler sees an excess of a certain outcome and interprets it as evidence that the underlying probability of that outcome might be higher than what was initially assumed. This is direct opposite of the gambler's fallacy, which incorrectly assumes a balancing out in the short term.
In sports betting, Bayesian models are often used to update the perceived probability of a team winning as the game progresses and new information becomes available, such as goals scored or injuries. In poker, observing an opponent's betting patterns and reactions, providing data that experienced players use to update their beliefs about the strength of the opponent's hand.
Even in casino games, if a player suspects a slight defect in a roulette wheel or pattern in a dealer's shuffling, each observed spin or hand or dealt becomes a piece of data that can refine their estimate of the true underlying probabilities.
However, it's crucial to understand the limitations. If a game's probabilities are truly known and independent, like a properly shuffled deck of cards or a fair roulette wheel, then constantly updating your beliefs based on recent outcomes won't give you a predictive edge. As one insightful commenter noted, Bayesian prediction helps when a probability is unknown. In fair games with known odds, it doesn't magically create an advantage. Most casino games are designed to enforce these known odds.
Casinos actively try to minimize situations where players can gain exploitable information that would allow for effective Bayesian updating. Frequent shuffling, using multiple decks, and concealing past plays are all strategies to keep the true probabilities as opaque as possible to the players.
Think of it like trying to guess if a coin is biased. Your initial guess, your prior, might be 50-50. Each flip gives you data and you update your belief about the probability of heads or tails. The more flips you see, the more confident you become in your updated estimate. Similarly, in gambling, each observed outcome can refine your understanding of the underlying odds but only if those odds aren't fixed and perfectly known.
Let's move on to Markov chains, a concept that helps us understand a process where the future depends only on the present.
A Markov chain is a sequence of possible events called states, where the probability of moving from one state to another depends only on the current state, not on the history of how you got to that state. It's a memoryless process. Mathematically, we can express this as...
The equation states that the future state of the process at time t little n plus 1 depends only on the current state at time little n, and is independent of the past history of the process.
This simply means the probability of being in state j at the next step, n plus 1, given that you are currently in state I, n, is the same regardless of all the states you were in before reaching state I.
A classic gambling example that can be modelled as the Markov chain is the gambler's ruin problem. Imagine a gambler starts with a certain amount of money, say $I. In each round of betting, they either win $1 or lose $1 with a fixed probability.
The gambler's wealth at any point in time is the state in this Markov chain. The possible states range from 0, ruined, up to some target amount, big N, their goal. The transitions are simple. From state I, the gambler can move to state I plus 1 if they win, or I minus 1 if they lose. Importantly, the states 0 and N are often considered absorbing states. Once the gambler reaches them, they stay there, either broke or having achieved their goal.
That's a nice way to put it, isn't it? Using Markov chain analysis, we can calculate the probability that the gambler will eventually reach the state of ruin. Wealth is 0, or as you said, broke, before reaching their target N. For a fair game of 50% probability, the probability of ruin is 1 minus I over N. This is a sobering result, as it shows that the gambler with limited capital facing a fair game is quite likely to eventually go broke if they play long enough.
If the game is favourable to the gambler, so with a win probability of greater than a half, there's a positive probability that they will eventually reach an infinitely large bankroll, in theory, avoiding ruin. However, if the game is unfavourable or even just fair, ruin becomes practically certain over time.
Many of the gambling scenarios can be viewed through the lens of Markov chains. The sequence of outcomes on the roulette wheel, though each spin is independent, the overall distribution of outcomes can be analysed. The changing composition of a deck of cards as they are dealt in blackjack, if we consider the count as the state, or even the progression of a craps game, can be modelled as Markov process.
In many casino games, we assume that the underlying probabilities reach a steady state. For example, after repeated shuffling, a deck of cards returns to a fixed random distribution, a stationary state in a Markov chain. Absorbing states, like going broke or hitting a jackpot and deciding to quit, represent endpoints in these processes.
Casinos use Markov models to stimulate games and assess risks. They might model the flow of money at a particular table as Markov process to estimate how often they expect to pay out versus collect, helping them manage their capital.
Think of a token on a board game that moves left or right based on a dice roll. Where the token goes next depends only on its current position, not on the sequence of rolls that got it there. That's a Markov chain in action. A gambler's bankroll, fluctuating with wins and losses, behaves similarly in many simple betting scenarios.
Now let's shift gears slightly and talk about combinatorial game theory.
Combinatorial game theory, or CGT, is a fascinating field that studies games of perfect information with no element of chance. Think of games like NIM or chess endgames, where all players have a complete knowledge of the game state and take turns making moves.
That's very interesting, but we're not talking about that right now. We'll do a different episode on that.
So our penultimate concept brings us to entropy and information theory.
In the context of gambling, entropy usually refers to Shannon entropy, which is a measure of the uncertainty of the randomness in a probability distribution. For a set of possible outcomes with probability P of I, and the entropy H of X is calculated as the entropy of random variable X, denoted H of X, is equal to the negative sum over all possible outcomes I of the probability of outcome I, P sub I, multiplied by the base 2 logarithm of the probability of outcome I log base 2 of P sub I.
The higher the entropy, the more random or unpredictable the outcomes are. For example, a fair coin flip has the maximum possible entropy for a two outcome event. Lower entropy means more predictability.
Information theory, pioneered by Claude Shannon, quantifies how much information you gain when you observe the outcome of a random event. A less likely outcome gives you more information when it occurs.
The concept of information entropy is central to understanding things like the Kelly criterion and the logic behind card counting. Shannon's work on information theory indirectly laid the groundwork for optimal gambling strategies.
The Kelly criterion is a formula that tells you the optimal fraction of your bankroll to bet in order to maximize your long-run growth rate. Assume you have an edge. The formula is the Kelly's bet size, F star, is calculated as F star equals P times the quantity B plus 1 minus 1 all divided by B, where F star is the optimal fraction to bet, P is the probability of winning, and B is the odds you receive. For example, you win $B for every dollar you bet.
The Kelly criterion essentially balances the desire for growth with the risk of going broke. It suggests betting a larger fraction of your bankroll when you have a bigger edge and smaller fractions when your edge is smaller.
Edward Thorpe, a key figure in applying mathematics to gambling, famously used Kelly criterion in his blackjack strategies, informed by discussions with Claude Shannon himself. Shannon reportedly pointed Thorpe towards John Kelly's work on information rate in betting scenarios.
From an information theory perspective, each bit of edge you have, information about a favourable situation, dictates how much you should optimally bet on that situation. The Kelly strategy can be seen as maximising the expected growth rate of your wealth, which is related to maximising the information gained per bet.
In card counting, every card that is revealed reduces the entropy or uncertainty about the remaining cards in the deck. A freshly shuffled deck has a maximum entropy. A card counter is essentially trying to exploit the situation where the entropy of the remaining deck is lower, meaning the probabilities of certain cards appearing are more predictable. They are gaining information about the deck composition.
Casinos actively try to maintain a high entropy in their games to prevent players from gaining a significant informational advantage. Frequent shuffling, continuous shuffling machines, and rules against discussing strategies at tables all serve to keep the outcomes as random and unpredictable as possible. Monitoring for card counters is also about preventing players from reducing the entropy of the game.
Think of entropy as the level of disorder in a shuffled deck, maximum uncertainty. Each card you see is like a bit of information that reduces the uncertainty. So let's say you get 5 of hearts. You know the probability of the next card being a 5 is?
Less.
Exactly. So it reduces the uncertainty. The Kelly criterion is like deciding how confidently to bet based on the amount of useful information you have. I think we gave away a bit too many secrets with all this explanation. It might be a safe bet to wrap up now.
Yeah, I agree. To wrap it up, overall, advantaged players can use sophisticated statistical tools to identify and exploit tiny edges, leveraging concepts like expected value, hypergeometry probabilities, Bayesian inference, and optimal betting strategies derived from information theory.
On the other side, casinos rely on the fundamental laws of probability and statistics, particularly the law of large numbers and the central limit theorem, as we discussed earlier on, to ensure the long-term profitability by designing games that are built in house edge and maximize the randomness of outcomes.
Yeah, and last but not least, it might sound a bit ironic, but our aim was not to promote gambling, but to educate you of the mathematical theories revolving around it.
You're only saying that because you went all in against me and lost all.
Yeah, but genuinely, gambling is not worth it, guys. Stay safe.
What happened to Mum? I didn't raise a quitter.
Yeah, I've had enough of it. Trust me, all gamblers quit before they win big.
Anyways, jokes aside, guys, do not gamble, and if you do, be mindful of these statistics and how they can be used against you. Thank you for listening, everyone.
We hope you enjoyed it and learned a bit more about the maths behind casinos operated, but haven't decided to start gambling yourself.
Like, share, comment, follow, share, like, comment, follow, and all that on all our platforms and social media accounts. See you in the next episode.
Goodbye.
Goodbye.